Here we have a linear system of algebra equations, not differential equations, algebra equations. The first equation being x plus 2y equals 3, second being 4x plus 5y equals 6. Solve it and graphically interpret the solution. Hopefully you've done this before, but it's good to get a little practice. There are numerous ways to solve it. Perhaps what you're most used to is what's called substitution. For example, we can take that first equation, x plus 2y equals 3, and, well, it'd be easier to solve for x in terms of y. Subtract 2y from both sides to get x equals 3 minus 2y. And then take that equation and substitute it into the second equation. That's why it's called substitution. Replace the x that you see there with 3 minus 2y. So we get 4 times, in parentheses, 3 minus 2y, that's what x equals, plus 5y equals 6. Simplify this, solve it for y. Hopefully you don't make a mistake. We need the distributive property here. 4 times 3 is 12. 4 times negative 2 is negative 8. Isolate y. First, combine these two like terms to get negative 3y. Also, subtract 12 from both sides. To get that, I did a couple steps in my head there, right? Negative 8 plus 5y is negative 3y. I also did a minus 12 and a to both sides to make sure I do the same thing on both sides. 12 minus 12 is 0. 6 minus 12 is negative 6. Divide both sides by negative 3. The negative 3's divide out. You end up with y equaling 2. You're not done. You also want to find x. Now substitute back up here. We do substitution a couple times. Replace y with 2. Looks like x equals negative 1. You should check your answers. Check your answer, I should say. There's one answer here, by the way. Yes, there are two variables. X is negative 1, y is 2. But that actually represents just one answer. The answer seems to be, if I've not made a mistake, the point with coordinates x is negative 1, y is 2. Negative 1, 2. You should check it. It's got to solve both equations. When you replace x with negative 1 and y with 2 in both equations, you should get two true statements. If x is negative 1 and y is 2, you get negative 1 plus 4 is 3. Yes. If x is negative 1, here you get negative 4, and y is 2. 5 times 2 is 10. Negative 4 plus 10 is 6. Yes, it works. Logically speaking, what you're really doing when you solve a system like this is you're really assuming there's a solution. You're assuming there's a point with coordinates x and y that satisfies both equations, and you're trying to deduce what that point would be if it indeed exists. It really is in the checking, like I just did 30 seconds ago, that you're really proving that it works. This derivation is not really proving that what you find works. That really is in the checking. Checking is more than just finding the right answer. It's proving that it really works. You can say this derivation that I did here, assuming I don't make mistakes, essentially proves there's no other solutions. Because again, the logic is I'm assuming there's a solution. If there's a solution, it must be that and nothing else. But in checking, you're proving it really does work. If that went by too fast, I'll be saying that kind of comments in later problems as well. As far as the graphical interpretation, you know linear equations like this have graphs that are straight lines. Maybe you prefer writing the equations in slope-intercept form. Most people do. With this first one, you'd get a slope of -1/2 and an intercept of 3/2. You don't have to do this, by the way. You can graph the equations without writing in slope-intercept form. Essentially by finding the x and y intercepts and connecting them with straight lines. You can find the x-intercept of this one, for example, by replacing y with 0 and solving for x. To get x equals 3. But we can also write each of these in slope-intercept form. The second one is a line with a slope of -4/5 and a y-intercept of 6/5. Should feel comfortable dealing with fractions, okay, not just decimals here. Real quick, but not necessarily super accurate sketch here. Intercept of 3/2, let's say that's right there, that's 3/2. Slope of -1/2 might look about like this. The x-intercept of that first one is 3, but I won't bother drawing it. This one, slope is -4/5, which is a little steeper negative slope than the first one. Y-intercept of 6/5, which is a little lower. This is 6/5 here. Going to be something like this. Okay, this is exaggerated. Say about like that. And that y-intercept is what is equals 6/5. The solution is this point. It's the point of intersection, coordinates -1, 2. That is the unique solution. You've got two lines that have different slopes. They're going to intersect at one point, so there is going to be one unique solution. Maybe you solve this also by something called elimination. I think for the sake of time, so you have some homework time here, I'm not going to solve it by elimination. Let me just say what you would have done. You might have, for example, multiplied this first equation by -4. Why? Because if you add it to the second equation, -4x plus 4x is 0x. The x's are eliminated. -4 times 2 is -8. -8y plus 5y is -3y. -4 times 3 is -12. -12 plus 6 is -6. You would have gotten this equation. If you did that elimination step, you would have ultimately gotten the same answer. So maybe that's how you did it. That's actually the main method that we'll use. Elimination in general is better than substitution. And we're ultimately also going to make the elimination process more automated, you might say, more efficient, by doing what are called elementary row operations with matrices. Okay, and maybe again, that's something that you've done in the past.